who to credit the question to. So now, without any further ado, I would like to introduce our speaker today. Marco Palma joined EPC in 2019, where he is Director of Motor Drive Systems and Applications. He has over 20 years of experience in motor control power electronics, ranging from switches to gate drivers, controllers, and algorithms. He is the author of several articles and patents in the field of motor control. Marco, thank you so much for joining us today.
Thank you, Renee. Thank you, everybody, for joining our webinar. So I will start the presentation. I hope everybody can see the screen. So welcome to the first installment of our summer series. This is the first webinar. There will be other three. In this one, we will discuss layout techniques. Layout techniques that are maximizing the performance of your GaN FET converter. So layout is a key factor in determining the performance of a converter. So first, we look at the various parasitic inductances present in a layout and their impact on their converter performance. With this knowledge, we can compare various layout design and learn which one are best, and present also additional details on how to design such a layout. Using that information, we'll be then in a position to look at alternative configuration and operating situation for which are best suited. After that, we'll look at the gate driver circuit layout and how to deal with the dual drivers ICs. Finally, we'll end this section by looking at how to use the same techniques to include a source shunt. The main parasitic inductance in a layout are the common source inductance, formed by the sharing of inductance between the gate circuits and the power circuits. So here is the gate, and here is the power circuit. Next is the power loop inductance that encompasses both FET and the decoupling capacitor. This is the power loop inductance. And usually when I talk about this, I refer to the high frequency part of the power loop. Lastly, there is the gate loop inductance, which are actually two circuits. One for turn on, where the current is going for the positive of the gate driver, then going to the gate, and then closing back on the negative of the capacitor. And then there is the turn off path. Turn off path goes from the gate and goes through the turn off transistor of the gate driver. Here we show the impact of the common, sorry, I had a problem in my presentation. Okay, now we are perfect. Here we show the impact of common source inductance on losses generated in the converter. And the graph on the right shows the common source inductance on the x-axis, so from 0 to 1 nanohenry, and power loss on the y-axis, okay? As the common source inductance increases, so do the losses generated in the converter. This is due to the slowing down effect on the gate as a result of the opposing voltage generated by the common source current during the transition event. The faster the transition, the higher the opposing effect becomes. The best method to overcome common source inductance is to eliminate it. And we show you how you can do it with layout. Next is the effect of the power loop inductance on losses generated in a converter. The graph shows the power loop inductance on the x-axis and the power loss on the y-axis. Okay, again in the nanohenry, the inductance. As the power loop inductance increases, so do the losses generated in the converter. This is due in part to losses resulting from the exchange of energy between the output capacitance of the FET and the loop inductance. The effect of power loop inductance can also be observed from the switch node waveform. The higher the power loop inductance, the higher the ringing amplitude. So on the left here, you can see 1 nanohenry, and then the right, the effect of the 400 picohenry, 0.4. The best method to overcome power loop inductance is to minimize it. And we show you again also how to do it with this layout webinar. Circling back to common source induced losses, we now plot on the same graph the both losses, common source inductance and power loop, emphasizing that the common source inductance is higher detrimental effect, and hence we always prioritize correcting common source inductance over power loop inductance. Finally, we'll look into the effect of the gate loop inductance on losses generated in the converter. In this case, there are two loops to consider, which are the turn-on loop, and you can see on the right, and then turn-off loop you can see on the left. In both cases, an additional resistance is used to damp out the effect of the inductance to ensure the ringing voltage peaks do not exceed the maximum in the case of turn-on, and also do not ring above the threshold voltage in the case of turn-off. As gate loop inductance increases, so does the resistance needed to damp the ringing. As the gate resistance increases, so do the transition time with corresponding increase in losses. The best method to overcome gate loop inductance is to minimize it. And again, we show you how to do it with the layout technique that I'm going to show today. So now that we know which parasitic inductance are at play in a layout, we can then begin to analyze various layout configurations. So first we'll present the lateral layout characterized by the main bus capacitor placed next to the FET, such that the power loop is laterally oriented in a plane. In this way, you can see from the red arrow. And it is in the PCB surface. This layout is popular among designers, and it's really used, especially in many MOSFET converters, because it's simple and intuitive. Next, we'll examine the external vertical layout, which is also popular. So the bypass capacitor are on the bottom of the PCB, and the switch are on the top of the PCB. So they are on the positive layer. And in this case, the loop from power is like this, and you can see it from top, how it closes and goes from one direction and closes in the other direction. This layout is characterized by the vertical orientation of the power loop, where the bus capacitor are placed on the bottom and the FET are on the top side. Finally, we have the internal vertical layout, also known as what we call the optimal layout. This layout has the bus capacitor just placed next to the FET, and the power loop is now formed vertically. It uses this first inner layer for the power loop return. So the main point here is having the first inner layer really near to the top layer, and then having the return just beneath the top layer. And from the top, you see how the current is flowing, especially the high frequency current. To better understand which layout will yield lower inductance, we need to understand how inductance is generated. Here we show a vertical layout with the bus capacitor placed next to the FET. Okay. In this example, we ask you to identify which layout has higher inductance. The left design with its long, narrow approach, or the right design with its short, wide approach. In both cases, the thickness will be kept the same. So I have the same thickness here, and I have the same thickness here. So I give you 5 seconds, 10 seconds, and think which of these has a higher inductance. Is the one on the left or the one on the right? And to answer this question, you need to remember the magnetic flux direction and the basic R-core inductor equation. Okay, so the inductance is proportional to the length, to the thickness. It is inversely proportional to the width. So if you answer that the long narrow approach is higher, then you are correct. You can see that this one, the length is higher, and which is the inductance is proportional to it, while keeping the same width. And the thickness is the same, sorry, the width is smaller. So this one has higher inductance. So wider, it's better. I give you another question, okay? Again, which layout has higher inductance? Let's shake up the design and let's compare the vertical and lateral design, okay? Which of these two designs has higher inductance? And in this case, I have the thickness is this, the length is this, and the width is this one. And this is the lateral, and this is the external vertical, okay? For the lateral design, the definition changed. So we need to adjust what we define as length and width. And then plugging those definition into our equation, then we can now see that width has become a very small value below the line in the equation. So driving a significant increase in inductance. Here, width is very small, and width here, the inductance is inversely proportional to the width. Okay. So if you answer that the lateral design has higher inductance, then you are correct. However, this is an incomplete picture because most lateral design will include layers beneath the main power loop. So we need to examine the effect of the plane that they have on the inductance. With our improved understanding of inductance, we can now revisit our three layout design and compare them. The lateral design is showing true to the equation at having high inductance, but not as high as predicted. And here you can see the lateral design on these green curves, and they change it depending on the inner layer thicknesses, okay? The fact that it's not as high as predicted is due to the first inner layer acting as a current mirror and canceling the inductance. So it's really the first inner layer is helping a little bit. It is clear that as the first inner layer moves further from the power loop, then its effect is an ever increasing inductance given the current mirror effect diminishes with distance. That's the reason why you see this increasing, the green curve get increasing. The external vertical layout is highly dependent on the thickness of the board. And so if the board thickness is increased, so does the power loop inductance. So here you see the external vertical as a red line, which is basically linear with the board thickness, because the area of this loop becomes bigger with the thickness. Finally, the internal vertical layout approach has the lowest inductance, given the main inductance cancellation effect that occurs within the first inner layer. So thus making the clear choice for the lower inductance layout. You have also to remember that it's important to have the first inner layer really near to the top layer, so that all the high frequency current is really going into this path, is not going anywhere else. That's the clear trick behind this layout technique. So let's get into the detail on how to design an internal vertical layout. So from now on, I will talk about what is the internal vertical layout. We also call it optimal layout. Again, first we place the component as close as possible to each other without violating manufacturability rules. In this example, we identify the gray trace as ground. So this is ground and this is ground. The red is the input voltage, the main voltage, okay? And the green is the switch node. We show here the top and the inner layer one layout with the placement of the FET and bus capacitor. So I'm just showing 2 layers. You may have 8 layers board, but just showing 2 layers. So next we place the vias as close as possible to yield the shortest connection path between the 2 ground connections. So this via are used to go for a very good connection for the inner layer one. Next, we then specify the thinnest possible substrate between the top layer and the inner layer one. And the reason, as I told you in the previous slide, is that you want to have the smallest loop possible so that all the high frequency is flowing into that. Then now we need to create a wide as possible path for the current by spreading out the vias as much as possible. So it's really important that the vias, because vias will have here also, will have some area around, you need to spread the V as much as possible so that you have the widest in this direction path for the current. And then this is going to give us the lowest inductance solution based on what we saw before. And also you can have other layer for sure. And here you have to remember that the inner layer one is not required to carry all the full current. All these tips, trick and tips I'm showing here is to really deal with the high frequency current that you have in a power loop during the switching. All the other current can be carried also by other layers, including other ground layer that will carry the middle frequency of the low frequency current. Now that we understand how to design an internal vertical layout, we can also look at alternative configuration. This can be useful when faced with layout restriction or improve the thermal performance of our design, as we show later in the presentation. So on the left, I'm showing a layout where the bus capacitors are located next to the lower FET instead of the upper FET. So here then you have V in, so this is the source of the voltage. Switching node is still in green, and the ground is in gray. And the inner layer is V in. If you compare to the previous, the inner layer was ground. On the left, I'll say, this can be used when you have this phases with layout restrictions, such as two-phase design. And then you need to have one phase made in one way, the other phase made in the other way. This can also improve cooling for the FET given the change in via structure. And this will be more clear when we will have a thermal webinar of the summer series, okay? On the right, we show a layout where the bus capacitors are located between the FET, and the return becomes the switch node. In this case, the switch node becomes buried between electrical quiet planes and thus can reduce EMI. Again, remember the green is the switch node, the gray is the ground, and the red is the input voltage, and the inner layer now is the switch node. It really depends on your layout restriction, on how many phases you have. You really can have this alternative layout configuration if you compare to the previous one, which I just shown one slide before. And that was this one where I had the return with the ground. Up to now, we have only discussed the power connection. Now we need to look at how to work with the gate signal and minimize the common source inductance simultaneously. So remember what I said at the beginning of the webinar, the common source inductance is really detrimental. So it's the first that needs actually to be eliminated if possible or to minimize. So in principle, we treat the gate circuit in the same manner as the power loop. Shown here, we have the gate signal on the top layer. Okay, these are the gate signal on the top layer. And in the gate return is on the inner layer. Okay, so we can have the gate return by using the inner layer. In this manner, we can also locate the common coupling point close to the gate driver and thus ensure lowest possible common source inductance. To further ensure low common source inductance, we also route the gate signal orthogonally to that of the power loop. So the power loop is going in vertical, so you can imagine the current moving from the top of the high frequency capacitor to the high side, then going to the low side, then entering back in the ground and closing here. So in a vertical loop, while the gate signals are rotating on the plane on orthogonally to the power loop. But this is also minimizing the inductance. Now that we can route a basic half bridge, we need to look at option with dual gate driver in a single IC, in a single integrated circuit. Why am I doing this? It's quite typical to get two-phase converter, maybe a two-phase buck converter as an example. And in this situation, it may be necessary to extend the gate signal length to reach the FET. So you need to always prioritize in the layout the switch and give the lowest gate loop inductance. In a case of a buck converter, but that's also true on a boost converter, one device is really working as a switch and the other one is working as a rectifier. Then the gate signal for the rectifier is less critical and so can be further a little bit farther away. So here in the buck, the hot switch is also called control switch, or it's really the switch which is doing our switching as the lowest inductance from the gate point of view, while the low side FET, which is mainly working as a rectifier, as a highest inductance, but it's less detrimental. You can, this is the same for a buck, can be done in the opposite way for a boost. Here is a boost, then in that case, in the boost, the low side device is acting as a control switch while the high side is working as a rectifier. That is valid for a buck and a boost. In a case of a more generic inverter, such as a motor control inverter, then you cannot rely on one switch being a rectifier and the other one being a control switch, because the current is always rotating. So it's better to equalize as much as possible the inductance of the gate driver. Next, we show an alternative layout configuration option for a buck or a boost converter. And for a layout design option 2 with a vertical based layout for the FET suitable for two-phase single output converter. So the difference, if you compare to the previous slide, is that now our power loop are horizontal, okay? This, if you look on the top on the buck solution, I have a power loop which is horizontal here and is also horizontal here, and the same in for the boost. And the return plane in this case for the buck is the V in, and also your wire in this case is the the ground. If you remember the previous slide, I just go back for comparison. The difference here is that we have vertical power loops, and then for the buck, for making the best layout, it's better having an inner layer return made of ground, and for the boost, the inner layer return made of input voltage. Instead, if you go horizontal, it's just the opposite. So up to now, we have discussed the standard half bridge topology. However, there may be situations where a design requires shunt in the source path of the lower FET. This is quite common, especially in motor drive, but not only. So you really want to know the current which is going to the phase by reading the shunt when Q2 is on. Essentially, we treat the shunt in the same manner as the high frequency bus capacitor. So we need to use shunt with the lowest possible inductance. Remember, we need to reduce all inductances, the common source inductances and the power loop inductances. And the shunt is just in series with both the low side gate and also the power loop, mainly with the power loop, because the gate low side can be closed directly to the source, but the power loop is there. And so we need to treat this shunt similar to the bypass capacitor here. So essentially, we need to either use, there are several ways to do it. So our preferred approach is to use multiple resistors in parallel, okay? And so that you can heal the low inductance shunt, as we have learned that short wide layouts heal the lowest inductance. Alternatively, you can choose also wide and narrow standard shunt like this one. You don't have to choose long, narrow shunt because these have high inductance. These ones are good if you put in series to the switch node, especially for those applications where the load on the switch node is inductive, but they are not good if you place them in series with the source of the low side. So remember, you have always to do either parallel, which is the easiest one, or finding the right wide package for the shunt with the lowest inductance. Adding a shunt to your schematics require additional consideration given the fast transition of the GaN FETs. First, we need to filter the power supply to the gate driver as it is no longer connected directly to ground at high frequency. Okay, so we usually use a ferrite bead. We may also use a kind of damping resistor. Then maybe we put zero ohm, or simply we can increase the voltage. Okay. Then also the PWM signal to the driver need filtering just enough to maintain signal integrity. Like MOSFET, GaNFET can have different turn on and turn off gate resistor values. Okay, so you can have two different resistors, but in this case, we can take advantage by moving the turn off resistance to the return path. So in this way, we have a better layout also. If additional filter is needed, then a capacitor can now be added without affecting the shunt impedance. And the choice of a gate driver must also look at drive levels and drive signal hysteresis and ensure that those values do not fall within the shunt voltage. And there are also other type of solution. You see this gate driver here has a common ground between the input and the driving of the low side. There are also some gate drivers where there is a decoupling factor here for the voltage, which is helping in this type of topology. And especially in motor drive applications, better using gate drivers also for GaN that have a different ground connection. Lastly, we still need to keep an eye on the common source connection point, as multiple paths can exist and must be taken care in the layout. Now that we have the schematic circuit needed to add a shunt in the source path, we can now plan the layout using all the internal vertical layout technique. So the technique is exactly the same as before, is an internal vertical layout. And so what we do, we start with the capacitor beside the upper FET, okay? And then we ground, in this case, is the high frequency return on the inner layer configuration. And since the common source inductance is the most important, we want to ensure that its location will yield the lowest possible inductance. So we now add the shunt next to the lower FET. Okay, and you see there are several in parallel, similar to the bypass capacitor. Okay, and they are put in a similar manner as the bypass capacitor. We can then route the gate signal to the driver position as close as possible to the FET. And lastly, the turn-off resistor and filter capacitor, if needed, can be placed next to the shunt and between the FET and driver to yield the lowest inductance. And you also have to take care of driving carefully signal Kelvin point, which are then covered by the ground reference for amplifying then the signal of the shunt resistor, so that you get away from the switching node and then you can amplify somewhere else the drop of the shunt resistor. So now we are at the summary and the end of the webinar, and to close the layout discussion, we have learned the three most important layout related parasitics, which are in order of importance: common source inductance, power loop, and gate loop. With that knowledge, we also presented various layout configuration and showed that the internal vertical layout, which also we call optimal layout, yielded the lowest inductance and hence the highest converter performance. Using the layout technique, we then presented the alternative configuration of the internal vertical layout, and with a supply or switch node as the return path. So you can have either the ground, or you can have either the input voltage, or you can have the switch node as a return. So it's not mandatory having only the ground. One thing I forgot to mention, but that would be a specific webinar, I will show you the webinar, is that once you get less swinging in your switch node, because you're using our internal vertical layout, which is also known as optimal layout, then you have less ringing, then you have less EMI, because the EMI is directly related to the peak of the voltage you're getting and also the frequency of the ringing. There are some additional resources. When you will get this presentation, you will have all these up notes and videos and reports that are talking about our device and especially special look with the layout. And last thing, just remember that this was the first webinar, and then there will be other 3 webinars coming on to close the summer series. And thank you for your attention. Now we can open the question and answer session. I give you back the control to you, Renee. Thank you.
Thank you, Marco. So yes, now we'll start answering some of the questions that were submitted during today's presentation. Just as a reminder, you can still continue to submit your questions by typing them into the Q&A feature at the bottom of the screen. So we had a lot of good questions come in, Marco. So let's see, the first one was, is a 2 kilowatt isolated DC to DC at 48 volts in unregulated full bridge configuration doable with GaN? And what would be the preferred way for heat removal?
Okay, for the yes, the answer first is yes. You can do the 2 kilowatt, and there are several ways, but we have a specific way to do the thermal management and the heat removal, and that will be discussed on this webinar, the last webinar on August 25. But I can anticipate, well, at least by voice, what is happening, and we suggest using some devices which are threaded standoff, which are mechanical device with a threaded standoff inside, so they can get placed by pick and place machine on a regular SMD process, and they get soldered on the board, and they are made so you can then screw a heat sink on top of the device, and they have the exact distance you need so that the thermal interface material between the heatsink and the device has the right thickness. And that's the most efficient way to remove the heat, and because you can remove it either with a, there are 3 ways to do it: passive air cooling with a heatsink, then you may have a forced air cooling with a heatsink, or you can have a heatsink with liquid cooling, depending on the application.
Okay. Do we provide access to any example projects in Altium and or KICAD?
We have several projects, several reference projects in our website. And usually what we give schematics and we give the Gerbers. And the reason is because then we sure that everything is done in the way we did it. But depending on special considerations, special condition and project, we use Altium. We may also talk separately and then exchange the Altium. Obviously, if we exchange the Altium project, we do it without taking any responsibility then if the final circuit of the customer doesn't work for some kind of version mismatch or some layout changes made by customer. And usually I do a lot of schematic review with customers and also a lot of layout review with customers.
Okay. What is the copper layer thickness for power and ground layer, and what is the formula for current calculation?
The copper layer, so usually what we do is we suggest using a 2 ounces copper layer internally. The reason is the external layers, the top and the bottom layer, usually they are 1 ounce because our device are a chip scale device with small bumps, and the technology, PCB technology, doesn't allow to have the required precision if you have 2 ounces. So the top and the bottom layer usually are 1 ounce, but the internal layer are 2 ounces. And the main reason to add in 2 ounces is because they can carry more current and they can heat less, and they can also remove the heat easier. I didn't get exactly what you meant by what's the formula for current calculation. So if you can explicit a little bit the formula, because which current are you referring to? The current that the plane can withstand? It is not clear to me.
Okay, so if you could just, yeah, type a clarifying question into the box, we'll circle back around to that. Which is better for the loop, C bypass, high FET, low FET, ground? Ground is on the top layer without vias, or use the inner ground layer with vias?
So if I have a bypass capacitor, high FET, low FET, I need to go back to read it, otherwise, sorry.
Okay.
Which is better? Okay, if I have a C bypass, high FET, low FET, and then ground, and ground is on top layer without vias, or use inner ground layer with vias? Yeah, no, absolutely. You need to make sure. Let me go back very quickly on the one of the first slide. So let me. It was a very nice slide, babe. Okay. Yeah. Where we are comparing. You see, it's really fundamental that you have the ground on the first inner layer. The reason is here, let me see if I can do a notation. Yes, I want to annotate like this. This is the plus, okay? This is the plus, V. Then if you imagine this, the red arrow goes through the up, and then the low device, so it's going on the top. And then if he has to close, it's better that he close in the inner layer immediately. And also you ask for the minimum thickness of a dielectric between the top and the inner layer, because then this area is what really matters. Oh, the bigger is the area, the higher is the inductance, the higher is the EMI, the higher is the EMC. So if you do something different, like having your ground somewhere in the same top layer, then you will have to do some kind of, from here, you will have to do some kind of things like this and things like this in the top layer. So making a very big area, and this is going to jeopardize your design. Okay.
Okay. What would be the impact of putting the gate driver in the opposite layer as the FET?
Okay, I'm doing this. It's not forbidden. Okay, it really depends on how fast you're driving your converter. So are we talking about, 2 megahertz converter with 25 volt per nanosecond switching node? Or are we talking about 100 kilohertz inverter for a motor with 6 volt per nanosecond switching node? Okay. If you put it, imagine like this, imagine this is the gate driver, okay? If you put the gate driver on the bottom, you will have some inductance before arriving to the gate. And as we show, the inductance is in the gate loop is detrimental. However, I did it, and if you need to do it, as long as you place the gate driver to minimize the distance of this gate going and return, then it's feasible.
Great. What would you advise for high current designs, paralleling multiple FETs close to each other? Oh, my question popped away. Hold on. Paralleling multiple FETs close to each other, or paralleling outputs of multiple separate half bridges with optimal layout per half bridge?
I'm trying to get the question again. So the answer is for sure, what you do with the GaN FET, you are paralleling half bridges. You're not paralleling the FET. So to give you an example by annotating here, imagine I want to parallel. What I have to do, I will have to put another hub up here, and another low here, and then I will have to put other capacitor here. And what you need to make sure is always that you paralleling half bridges and you keeping your layout, okay, and not simply paralleling the devices and not following the main rules. And the other thing which is really important is that each will change the color. Let's put it in this color string. Each device has to have its own resistors and back and forth, R on and R off, going to the gate driver, okay? And it's really important to equalize. Imagine the gate driver is here. It's really important to equalize the path from the gate driver to each device, so that if this is longer, then this one should become a little bit artificially longer so that they switch on at the same time. So the more parts you're putting in parallel, the more, let's say, difficult becomes. But we have a customer which are doing 12 devices in parallel per switch. That means 12 half bridges in parallel. And what we start doing, things to make sure. What you really need to make sure, you have to think about in where you start from the gate driver, that can be on the bottom of the PCB, and how the gate signal is going to go to all the half bridges in a kind of equalized way.
So while we're talking about gate drive, there's a question for the gate drive. You mentioned it was returned to the inner layer. This implies a via. Why is this better than going to source on the lower FET direct with no via?
Okay, yes, there's let me go on directly into the same. There's no, actually, there's no, let's say, counter effect. Can be done also on the same layer, okay? The reason is if you do it in the return, you may reduce a little bit the inductance, but that, I suppose, this is the slide we're talking about. So the gate connection here, then the point is that for the hub FET, the switch node is the return. For the low FET is the ground, the return. So at a certain point, you need to have one via somewhere, because you see here, this is the switch node in the inner layer, and then you have this one is going to be also part of the ground of the floating well of the gate driver, which is the reference for the I side of the gate driver. That's why you need to connect it in this way. It's the floating ground for the I side, and then if you want to shield a little bit the gate driver, then you're gonna have this type of via, but that's not really mandatory.
Okay. Do you have an example for a three-phase inverter?
Yes, the example for a three-phase inverter, actually, I released a Bodos Power article that was published in June. So if you look for Bodos Power June issue, you can go on the Bodos Power website. I think also in our website. In our website, there is all the recent publication. Then you will see an example of a three-phase motor inverter with also shunt, both in phase and also in the leg shunt, so that you can choose which one to use. And the three-phase inverter has basically the same concept you see for each of the half bridges. And what you can have is that each of the switches Usually what I put one half bridge here, then the other half bridge on the top, and then the other half bridge in the bottom, and then the three phase are going out on the right and going to the load, which may be a motor. But I recommend you to look on June issues of Bodo's Power article. You will find an article about it.
Okay. For the rectifier FET, having higher gate loop inductance makes it difficult to keep the FET off in case of SW transition, for example, when the SW flies up in the case of a buck. How is this solved if the gate loop is optimized for only the control FET?
Remember one thing, let me go, what that's really important on when dealing with GaN FET is always using a gate driver which are made for GaN FET, okay? So a typical GaN FET gate driver has, in this schematics, it doesn't show up. I'm looking if I have a typical gate driver for a GaN FET has two outputs. One output is to switch on, and let me go in. Just one moment. I'm going to pick the right slide so I can write on top of it. Okay, let's resume share here. And here you see in reality a GaN FET gate driver. If you consider this part, let me change color, otherwise you can see. If you can consider this part in reality, let's design it here. He has two outputs, one to switch on and the other one to switch off. And they go to the gate of the gate driver, okay? And the reason why you have two out, that means you have a pull-up MOSFET inside the gate driver here, and then you have a pull-down MOSFET to the gate driver here. That it means that this resistor here is definitely smaller than this one. So within the GaN FET, usually what you're doing is that you're doing a kind of the lowest resistance when you have to switch off, or actually is the other one. When you have to switch off this air gate here is smaller because you have two resistors, and one is the one for switching off, and this is a kind of a Miller clamp. So even if this node is going up, and then you have your Miller capacitance, this is not going to influence your gate of the low side, also because the ratio of Chi GD and Chi GS is less than 1 in GaN FET from EPC. So that's not really an issue.
Okay. How do you measure the VGS and VDS when you use a very compact layout?
Black magic. Very difficult to do. VGS especially, what we usually recommend is using high bandwidth isolated optical probes. And also it's then difficult, depending on the frequency you're going, it's then difficult because if you do a specific layout, then it's difficult to measure, okay? Because whatever you do, you're going to slightly change the capacitance of the loop or inductance of the loop. But the best performance I've seen so far is with the probes made by optical probes, which are able to measure the VGS of the I side while it's switching and is floating up and down in a converter. But it's not really easy. It's always difficult.
Okay. Are there any plans for EPC to integrate the gate driver with the power FET, as it would reduce the gate loop inductance even further?
Yes, absolutely. We did it.
We did it. Yes.
We did it. We actually have different integrated circuits. What we've been doing, both low side with the gate driver inside, and also half bridge with the full half bridge. So high side and low side, and also both FET to switch on the low power and high power, low side and high side power GaN FET. We have a device which is called EPC 2152, which is doing exactly this. And I'm I'm using on a 400 watt motor drive. I use 3 of them, and then I have a 400 watt, very compact 400 watt motor drive. It can be used also to do 400 watt converter, not just for motor drive. Yes, that's what we're doing.
Are there any app notes that show loss factor effects based on a switching frequency of 500 kilohertz instead of 1 megahertz?
Application notes on that, I need to dig in. I don't remember. What we should, for sure, we have on the website, and then I can show. We have on our website. We have. I'm going one quickly to the website. Just one moment. Give me the time to open it. I close it. And we have a simulator, and the simulator, it's working quite well, and there you can change. So this is our website. If you go into design support, and then you go into tools and calculator and tool selection, then let's make a clear example. Here you go and say I'm running 500 kilohertz, let's say 125 degrees, and a converter 48 to 12, 120 watt output, and then this is going to work at 500 kilohertz. We can also use, I don't know, 2.2 microhenry. And then it's telling me that I can use the 2204 on the top, and that's what is going to dissipate. And I can use, again, the 2204 on the bottom. This is what is going to dissipate, basically less than 1 watt on this one, and what was 670 on this one. And then you say, okay, but what about if I change and go into 1 megahertz? Then boom, I just changed this number here. I can even change the date time. If I go 1 megahertz, most likely I'm going to go into 0.9 microhenry. And then by looking into this, I see, okay, then now things are changing. The control switch is, if I keep the 2204 as an example, is doing 1.1 watt. In this case, maybe it's better using the 2052, which is doing slightly less, 1 watt. And then you can see what is 2204 again is 1.36 on the bottom. So that is giving you an idea on what you're going to get.
Okay. So circling back to that early question about the current, what was the formula for current calculation? It was plain current.
The current for the plane. Okay, yeah, there are. I don't remember by heart. Usually, what I do, I use the physics formula, which is telling me that the resistance is the resistivity multiplied by the length and divided by the area, and the area is the section of the plane. So if you have 2 ounces plane, the section will be double than having 1 section plane. That means your resistance will be lower. But usually what I do for that case is there are a lot of websites that do this calculation for you. Even the CAD, like Altium and things like that, they can do it. But usually I go on a website and I look on PCB trace current calculators, and then put the numbers, put even the temperature, which is important, is slightly changing the current, and then from that I get how wide has to be how the 2 ounce plane to bring away, I don't know, 10 amps, 20 amps, 50 amps, and so on. And from that, then you realize how many planes you have to put or how wide you have to be.
Okay. Could you go to slide 17? There's 2 questions specific to slide 17. The first one is, why is there no ROFF on top switch?
Okay, let me go to slide 17. I just realized that most likely when I showed the calculator was not sharing my screen.
Yes, you are. We can see it.
Okay, perfect. So now I pause the sharing. Go one moment back to the presentation slide number 17, so that we see 17 here. Okay, then we make it bigger and resume share. And then the question here, why I'm not showing ROFF? Yeah, you have to imagine here you have R off here, okay? Or you have to imagine that the gate driver usually have two outputs, so R off is going like this, okay? So the main point, let me clarify better. Usually the gate driver have two output for the GaN FET. So you will have R off like this. And the main point of this was that in this case, you can have R off connected directly like this, because then you will have R off on the return. Okay, it's just a kind of technicality, but for sure you have both.
So we do have quite a few more questions coming in. Are you okay to hang around for a little while, Marco?
Yep.
Okay. Second question on slide 17, how to filter the PWM signals when gate driver isn't differential ended?
Yeah, that's what we're doing here. That's usually the main problem is this. Okay, if you have a shunt, then when the current in the shunt usually is coming with some inductance associated with it. So when current is changing here, then you have a peak here. You can try to filter a little bit, but this is going to be a bounce here. And then what we suggest is having RC like this, so that you make sure that these thresholds are not causing unwanted turn on or turn off. It's not really easy. The best thing is, if you have a severe problem, the best thing is having so you have low side with the commands, and then you have your high side with level shifter, and then you need to have also level translator here, so that the low side ground is really decoupled from the ground signal ground. So you have two different, and this one actually you don't connect to the power ground. You may, it's just the return of your GaN FET, and then you can put whatever you want here, because then as long as this gate driver can withstand the imbalance, and usually the imbalance is plus minus 5 volts, so it's okay, then you don't have problem. If you instead are forced to use this type of gate driver where the ground is the same, then you need really to assess how much ground bouncing you will get by every commutation. So the faster here is the commutation, the faster is the IDT, the bigger will be the peak, and the highest the problem you can get in your system.
Okay. Okay, so we're going to continue to answer questions because there's still some really good ones here in the chat. If anyone does have a hard stop, you will get an email within 24 to 48 hours with a copy of the recording of the presentation. So you will not, you'll be able to hear the questions and answers that you may miss. So we will continue on. How do you determine the power loop inductance? I use Q3D, but they don't consider inductance inside the power device. So I think that's not accurate.
What we do is like this, we go, I think there is a nice slide, and that's something also you can do, at least you can do on existing, let me go to the slide, then I can talk. One moment. You can do on existing layout, and then based on that, you can understand what is going to happen on other layout. I would say it's difficult to predict, but there's one thing. If you have already a layout, the first thing you can do, you can go here and measure this ringing and the frequency. From the information of this ringing and the frequency, you get information on what is your loop parasitic inductance. And then you need to create a model based on the equation that we shown before, so that you can estimate how much you will be getting. And I tell you that if you follow our optimal internal vertical layout, usually you end up into this range, into 0.4, 0.5, quite common, as long as you have access to good PCB technology. If you start telling me that, oh, I have less layers, I cannot have a very thin um, um, uh, dielectric between copper planes and so on, then you're gonna enter into some kind of calculation that's better doing it, because in that case you need to assess what you're going to get, and then you have to simulate and see if what you're going to get is going to give you a problem in the converter. But it's really, I don't want to say it's a trial and error. It's a mixture between prediction made based on formulas and experience based on the real field by doing measurement and assessing. That's why we have these numbers here.
For 200-volt GaN, what is the recommended minimum distance between the top and inner layer?
Oh, that is really depending on the dielectric capability. The dielectric capability of the FR4 is quite good. So that's something you need to ask to your PCB manufacturer. But usually what you do is using the minimum, which is that can withstand the voltage that you need to do. Inside the PCB, usually there's no big difference. Where are the differences? When you are outside and you have to keep bigger creepage, because you can have moisture or other problems. But it's better asking for your PCB manufacturer.
Okay. I noticed you put vias under cap pads. Is there any solder reliability impact?
Yes and no. So let me clarify one thing that was not clear in this presentation. When we do, let me go exactly to the slide. When we do vias, and I say, okay, you can do vias. If we put it on pad, then it's better doing what we call via in pad plated over. Okay. So if you do like this, as in the picture, like here, if you look this here, the via in reality is not really on the pad, is on the trace. Okay. If you have two choices. If you spend a little bit more on the PCB, then you can put via directly on the pad. And what you have to do, you have to ask your manufacturer to do what is called via in pad plated over. That means if this is the pad, the via is inside, and then what happens is that they will fill it completely and they will plate it over, then will basically disappear. You don't see it. It's there, but you don't see it, and that's perfect coplanarity. This is costing you more, but it's giving you the best performance. If you cannot do it, then what you can simply do is, this is, let's say, your pad, exactly where the device is going to go. Then you place the via just near to it, and then connect it. And then in that case, you don't have a reliability problem, and you don't have to ask for the via in pad.
Okay. Is it advisable to put CM chokes or PI type filter at the input of the gate driver?
No, absolutely. The gate driver going to the gate must be as much as possible. First of all, the driver have to be two outputs, so that's the recommended gate drive for. These are the recommended gate drive for GaN FET, and these two output, one is for to switch on, the other one is to switch off, and then having just a resistor. Even if you want to have resistor 0 ohm, then put 0 ohm. Okay, that's important. Look, this will be discussion of next 2 weeks. So it will be exactly about gate drivers, and in that case, the reason is you have to have the cleanest possible path to the gate with the resistors and nothing else. Things like are done in a typical MOSFET arena. You have a resistor, then you have a Schottky diode, and then you have another resistor, which is usually smaller. So then when you switch off, this path will prevail, and then you have a lower resistors here to switch off and a higher resistor to switch on. This is not good for GaNFET. The reason is this one is already 0 point something, let's say 0.3 volt, and the threshold of a GaNFET is definitely smaller than a threshold of a MOSFET. So just by putting this, you're jeopardizing the possibility to Miller clamp the gate. So better having always a gate driver with double output, which is made for GaNFET. So the output really it's separated like this. And so you have the pull up and pull down transistor inside the gate driver, which are separated. And then this one goes to switch on and this one goes to switch off. And this is the only things you're going to attach to the GaNFET.
What about putting FETs on both sides?
I don't think it helps, because if you put FETs on both sides, first of all, you have also a thermal problem, because how are you going to remove the heat? The EPC GaNFET are in chip scale package, and they are very efficient if you are able to remove the heat from the top, okay? That means you're putting something, you will see in this thermal management of GaNFET, something connected to it on the top. If you put GaNFET on both sides of the PCB, then you need to remove the heat from both sides, and also the impedance between the two part of the PCB are too high, especially in high frequency. It doesn't help doing it.
Okay. Why is the hard switching gate loop more critical than the one for the GaN acting as a diode and risking induced turn on?
The hard switching, let's put it in this way, it depends on the application. But when you're doing hard switching, what happens is that you have, imagine you have a low side recirculating, like, because you switched already off the channel, and then the current is flowing in reverse conduction mode, and then you switch on the high side. Then you're doing hard switching. Depending how fast you're doing, you will have the steepest DVDT of your system. And then this is going to induce current here and induce current also here. And so it depends on what you want to achieve, how fast you want to be. Reality, what I usually do, I try to treat both gate in the same way, independently of the fact that I'm doing a buck or a boost. Or in an inverter, you cannot, every switch is working on a 4 full quadrants, and then there's no gate that you have to prioritize. So most important thing is when you switch off instead of the high side and the back, then it's the load which is commanding the DVDT, and the DVDT depends on the output capacitance of the GaNFET, and depends also on the output capacitance of the other GaNFET, and the current was flowing in the inductor, and also the capacitance of the inductor. Then it depends how much is the current and how much are these capacitance. Then maybe the DVDT of the 0 volt switching is going to be faster than the hard switching. It really depends on the case.
Are there any plans for a higher current FET plus driver with LVDS than the 10 amps that we have now?
We're working on it, because we have a lot of requests about it. So yes, stay tuned. As soon as we have news, we will let you know for sure.
Okay. Has GaN FET already been used a lot for PFC circuits?
Oh, you're asking to because here I'm doing a lot of DC-DC converter, and I'm also doing a lot of motor inverter, a little bit less than on PFC. Usually what is happening in a PFC is that GaN FET from EPC have so far the limitation on the maximum VDS voltage. We do low and medium voltage devices. On a PFC, usually you use a 650 volt device, which we don't have. So what we're doing, we're working on several concepts with universities on multi-level PFC, where then you get up to more than 99% efficiency, but at the price of the higher complexity of the system. Because while in one case you can do I don't know, simple boost PFC, in the other case you have to do a multiple level made with GaN PFC that is a little bit more complex. So it's not yet taking over too much, and the reason because it's mainly related to the multi-level topologies, which spreading right now. Maybe they will become more popular within within 5 years. That's what I believe.
We have one last question. Will any of these GaN devices be offered in standard packages like TO220 as a drop-in replacement for the field? I mean, you can expand on this, Marco, but really, regardless of package, they're not really drop-ins ever, right?
Right. The main point is GaNFET is not a drop-in replacement of a MOSFET. The only drop-in replacement of a MOSFET is a cheapest MOSFET drop-in replacement of a MOSFET. GaNFET is going completely different direction, is changing the system, is improving the system properties. So if you're going to take a MOSFET inverter or converter and just remove a MOSFET and put a GaNFET, you have only two chances. Either it works in the same way it was working the MOSFET inverters, if you're lucky, or it will work even worse. Okay, so it's not really the way to do. And the other most important thing is the TO220 package, I think, is the highest inductance package you can find. And then you jeopardize completely what I just shown today. And then what you get is a lot of ringing, a lot of power dissipation. You will get no advantage at all. Here we're talking about very fast transition that you have to manage in the right way to avoid any EMI, EMC, and then to get the advantage of the fact that you have this fast switch. So you have to minimize the inductance to the bare minimum, and that means package has to be either chip scale package. So then I can answer also one question just came in here, which is basic silicon. Our technology is a silicon wafer. On top of it, we build the gallium nitride circuit or discrete device, and then we glassify everything. So it's really the silicon is just a mechanical carrier, and it's also thermal carrier. Is not really involved in the electronic conversion, and that's material package for the eGaN is a silicon. And there are already in the field other companies which are doing similar things as what we're doing. And the reason is to simply reduce to the bare minimum the inductances. Otherwise, you don't get any advantage.
Great. Well, thank you, Marco, and thank you for staying over time. And thanks for everybody else for all the great questions and for staying over time as well. We will, if you have any additional questions, please feel free to send them into info@epc-co.com. As I mentioned, you'll receive a follow-up email within the next day or two with a link to view a recording of today's webinar. And lastly, be sure to register and attend the remaining installments of the How to GaN Summer Series. You'll have an opportunity to earn reward points over the course of the entire series. So our next one, as you can see, is in 2 weeks on July 28th, where we'll cover gate drive techniques and the IC ecosystem for driving GaN FETs. Please visit the website at epc-co.com for more information and to register. Thank you for joining us today, and have a great rest of your day. Thanks again, Marco.
Thank you, everybody. Bye-bye.
Bye.